Hello, this video accompanies our discussion of multicollinearity. So first I want to show you an example of a factor that likely is not confounding. And so this is the Wooldridge GPA data on 141 students from Michigan State. And so the variable that I'm interested in is, do you have a boyfriend or girlfriend? So first let's do our simple linear regression. College GPA is a function of skipping class. And this is our naive estimate that skipping one additional class per week is associated with a decline in GPA of negative 0.09 points. So now let's add in having a boyfriend or girlfriend. We may think this is confounding, that it's linked to both GPA and skipping class. Let's add this in. And as you can see, hardly anything happens to the coefficient on skipped relative to the naive one. So this provides very little evidence that having a boyfriend or a girlfriend is a confounding factor. And so this can stem from one of two things. One, it's uncorrelated with college GPA, and we can pick that up by looking at beta 2 hat. Well, this is 0.07. It's kind of similar in size to skipped, so it seems unlikely that the lack of bias is coming from beta 2 hat being 0. More likely coming from delta 1 tilde, and we can see this by regressing x1 on x2. And indeed, in this case, we get a very low coefficient. Right, so this is an example of something that's not confounding. Now I want to do an example of perfect collinearity. So it turns out this data set does not have freshmen. And so I'm going to estimate college GPA and skipped as a function of being a sophomore, a junior, a senior, or a fifth-year senior. Notice that senior 5 is omitted. And the reason why is that if I gen total equals sophomore plus junior plus senior plus senior 5, and then I sum total, it equals 1 for everyone, which means that 1 minus junior minus senior minus sophomore equals being a fifth-year senior. So there's no variation left after we control for all of these other categories to estimate the beta on this coefficient, which is why Stata decides to drop it. So now let's look at multicollinearity, which is the problem of variables that are highly correlated, but not perfectly so. So as I mentioned in class, an example in this data set is, let's say, living on campus. Okay, so let's see, we think that's correlated with student motivation. So that's going to be associated with college GPA and skipping class. Okay, and indeed we see a change in the coefficient right once we add campus. But then we also notice in terms of proximity to class, there are a bunch of other variables. Do you drive? Do you bike? Do you walk? And so we see this and we decide to add all of them in. Drive, bike, walk, do you live in a fraternity, right, in terms of living on campus. So we throw basically everything in that we can think of. Notice, in fact, one of these is perfectly collinear, right? If you don't drive, then you're either biking or walking. And so what happens to the standard error on campus? It goes up. Not dramatically so in this case, right? But we definitely lose some precision by adding in all of these variables. And the question we need to ask ourselves is, do we really need all of these? Are they capturing what we want? Do we want to use our fairly limited variation because we only have 141 observations to estimate all of these coefficients, or would one or two be sufficient?